A central power station generates electricity at thousands of volts, yet residential neighborhood requirements are much lower, typically 120 or 240 volts. Transporting energy between the station and the consumer requires pushing electrical current through miles of conductive wire. Every meter of that wire resists the flow of electrons. This is the math of joule heating. The power lost in a conductor equals the square of the current multiplied by the wire's resistance. This lost energy radiates outward as wasted heat. If the voltage is not modified, the current must be high to meet power demands. If a cable has 5 ohms of resistance, attempting to send 10 kilowatts at 240 volts results in an 87% energy loss before the power reaches the destination. Attempting to power a widespread electrical grid at low utilization voltage is a physical impossibility. The thermal losses would consume nearly the entire output of the generating station. The engineering solution involves modifying the electricity for transmission using a step-up transformer. This shows the ideal transformer identity. It defines the fixed mathematical relationship between voltage, current, and the physical turns of wire within the device. According to the law of conservation of apparent power, total power must remain constant between the input and the output. Because power is the product of voltage and current, these two variables are inversely proportional. When a transformer steps the voltage up to 400,000 volts, it forces the current down proportionally. Because joule heating is tied to the square of that current, the thermal loss in the transmission lines drops to near zero. This mathematical decoupling of voltage and current is the mechanism that enables modern long-distance electrical infrastructure. To see how this relationship is physically achieved, we start with a theoretical model: 2 isolated, unconnected copper coils in a vacuum. When an alternating current passes through the primary coil, it generates a magnetic field. Because the current is an AC waveform, the magnetic flux constantly expands and collapses as the polarity reverses. This behavior is the basis of electromagnetic induction, a phenomenon first discovered by Michael Faraday. Faraday's law shows varying magnetic flux induces voltage in nearby conductors. The primary field drives an electromotive force in the secondary coil. This voltage scales with the wire loops. Doubling the secondary turns multiplies the output voltage. Faraday's original 1831 implementation used 2 separate coils of cloth-wrapped wire wound around an iron ring. While this model demonstrates the principle of induction, it ignores the thermodynamic penalties inherent in moving energy through physical materials. The first constraint of our theoretical model is that air is a poor conductor of magnetic fields. This leads to leakage flux. Magnetic lines disperse into the surrounding space, missing the secondary coil and wasting energy. To fix this, engineers insert a core of high-permeability silicon steel through the center of both coils. Steel provides a path of low magnetic reluctance. It captures the flux and confines it to a closed loop, ensuring nearly all the energy from the primary coil reaches the secondary. However, introducing a metal core creates a new thermodynamic penalty: hysteresis loss. The AC current forces the magnetic domains within the steel to reverse their polarity 50 to 60 times every second. This constant molecular motion creates friction, which is dissipated as heat within the core. Solving flux leakage binds the system to an inescapable thermal cost, illustrating how efficiency in one area often creates a physical penalty in another. The conductive nature of the steel core also introduces a secondary internal challenge. Faraday's law induces current in any conductor exposed to changing flux, and the core is a large block of conductive iron. The magnetic field induces swirling loops of electricity inside the core called eddy currents. Left unmanaged, their heat could melt the entire transformer. The solution is lamination. Engineers slice the solid core into thin steel sheets. Microscopic insulation separates each sheet, preventing current from flowing across the core and increasing resistance. This breaks the massive eddy currents into tiny, weak ellipses. These restricted paths cannot generate destructive heat, allowing the core to remain stable. Mechanical lamination is required to exploit the benefits of an iron core while surviving the parasitic forces it creates. To complete the build, the laminated core and copper windings are sealed inside a heavy steel tank. At the scale of a megawatt-level grid, even a 1% efficiency loss generates enough sustained heat to degrade the unit's internal insulation over time. High voltages also create the risk of corona discharge, a blue electrical arc that can leap across the gaps between internal components. To manage both threats, the tank is flooded with highly refined transformer oil. The oil acts as a convection coolant, rising from the core to external radiators before sinking back down. It is also a dielectric insulator. With a breakdown voltage exceeding 28 kilovolts, the oil prevents electrical arcs between the high-voltage coils. Modern units have transitioned from toxic PCBs to biodegradable natural esters that offer high fire points and stable dielectric properties. Without this chemical bath, the thermodynamic stresses of grid-scale transmission would destroy the machine. To use these machines effectively, engineers must translate these physical losses back into mathematical models. This translation was pioneered by Charles Proteus Steinmetz. This is the Steinmetz real transformer equivalent circuit. It uses specific symbols to account for every physical flaw we have addressed. The symbol RC represents the energy loss to core heating, while RP and RS map the resistance of the primary and secondary copper windings. This model allows engineers to design systems that anticipate and manage the inescapable physical costs of power transfer. On the grid, these machines operate within high-voltage substations, often for 50 years or more. They take the output from generating stations and step it up to 400,000 volts for transmission. The power travels across the country with minimal heat loss before being stepped back down for safe use in homes and businesses. This process requires the industrial assembly of thousands of optimized cores and windings to sustain the national infrastructure. By balancing the ideal mathematics of induction against the thermodynamic realities of the hardware, the transformer enables the stable, continental-scale distribution of electrical power.